Mass and energy balance for biosystem. Module 12, carbon balance and storage. Segment 2, mathematical models. It's Lily from School of Life Sciences and Technology, Institute Teknologi Bandung. In the previous segment, we already discussed about the introduction, and for this segment, we will continue to the mathematical models. Mathematical models of biogeochemical cycles can take on various forms depending on the level of detail or necessary or on the type of supporting or verifying information or data available. In general, models attempt to relate the rates of transport, transformation, and input of substance to their masses and change by way of equation based on material or energy conservation principles. By far, the most common models employed for biogeochemical cycles are lump models. Lump models are sometimes referred to as black box models, so called because they consider only the inputs and outputs of the boxes and their interior masses. They do not explore the interior details of box, such as the predator-prey interaction that influence the population dynamic within the biota, or the complex ocean chemistry that affects the air-ocean exchange or material. Calculation for a model of the carbon cycle. In this figure, we will use a schematic diagram similar to that in the figure 2 to construct a mathematical model for the carbon cycle. In this figure, a simplified representation of the carbon cycle, including an input from fossil fuel burning. And our purpose is to estimate the effect of fossil fuel burning on the level of carbon in the atmosphere. This is the important information for the assessment of the greenhouse effect. Based on the figure, we can get the following equation that relate the flow rates or flux in the diagram to the mass of the carbon in the box. The following equation we got from some references, and the numerical value of the coefficient were derived from data presented in this reference. For the FA is an input disturbance, and in this equation also for the masses are in unit of petagrams, and the flux or F are in units of petagrams per year. Material balances on carbon can be written for each of the box in figure 3, for example, with the information in the equation 1 to 6 incorporated, the unsteady balance on the atmosphere box is given by the following equations. Based on the figure 3, similar balances must be added for the other three compartments, and initial value for the force M must be given to complete the mathematical models. The input from fossil fuel consumption, the disturbance function or F, may be constant or a function of time. Its current value is about 5 petagrams of carbon per year. Over some periods of time, its value increases at the rate of about 4% per year. The steady-state model is derived simply by setting the time derivatives in the transient equations to 0. Further, we can deduce from a physical consideration that no steady state is possible unless F is 0. Notice that the steady-state equations are nonlinear in the m's owing to the exponents on ms and ma. Consequently, the numerical search procedure must be used. According to the numerical value for flux and reservoir level of carbon, the effective time constant for the reservoir vary from a few years for the atmosphere to hundreds or thousands of years for the deep ocean layers. Therefore, a large input into the atmosphere may eventually decay to only a modest, permanent increase owing to the fact that the large capacity of the oceans will eventually absorb most of it, but the effects on the atmosphere may be felt for a century or more. In this case, for the unsteady state, the same is true for the steady state, which is the being nonlinear, cannot be solved analytically. For the next segment, we will discuss about the carbon stage. Until then, I'm Lily from Institute Technology Bandung.